I think this laser battery's running on. Each page.
All right, ladies and gentlemen. Again, very close to. These two, Melani and Orin, have been working with me quite extensively over the past 6 weeks. I got them to do a pretty large scope engineering project concerning the safe reentry and landing of a simulated rover. So, take it away, guys.
Okay, so I'm Melani Spath.
I'm Orin Miller.
And our project is called How to Land Your Rover. Okay, so the first video we're watching is on the two Mars rovers, Opportunity and Spirit. These two are twins, so they're identical in every way. And we're going to show you the landing sequence so you can see sort of kind of what we're trying to do when we're landing ours off the roof. So the first step, as it starts to re-enter, you can see the heat shield protecting it from entering the atmosphere. And then the first step you'll see is releasing the parachute, which is pretty typical because air resistance will slow it down enough. And then the next step is releasing the heat shield. And at this point, we'll actually be able to see the rover, and that's the actual rover. And then next it's going to deploy the parachute, or the airbags, which will allow it so that when it drops it, it'll just bounce around on the ground, and that's supposed to prevent the instrumentation from being broken. And so, as the rocket boosters slow it down enough to just drop it, it's just going to bounce around like a bouncy ball. And it's not a very predictable method of landing though, because depending on where it hits and what it does when it lands, it won't land in the same spot if you do several trials. And so the picture on the left, you can see the instrumentations on here they're very fragile, which is why you need a good method of landing the rover. And then this, you can see the airbag right before it was about to drop it on Mars. So then this next video is another rover called Mars Science Laboratory, MSL, or Curiosity. This rover has a different method of landing in that it focuses more on the rocket boosters than on airbags. It doesn't have any airbags, and it still uses a parachute though. And so the first step's the same with the parachute releasing, because that's really key that's the first step of slowing it down during its descent. And so after the parachute, the same thing, the heat shield is released. And then this is where it starts to get interesting, the rover. This one has the wheels come out, and so then that way it's just going to set it on the ground as opposed to dropping it, which is a lot safer. So then when it finally releases, now the rocket boosters are slowing it down enough to land it on Mars. So the next step is going to be the sky train. You're going to see cables lower down the rover so that it requires less fuel to set the rover on the ground. And then that way when it sets it down, it can set it down very slowly and precisely. And this is more accurate because it'll know exactly where it's going to set it down beforehand, and it won't be in risk of hitting a rock or something when it's dropped, as the parachute method has had that risk. And so on the left still you can see the instrumentation and the wheels and that, and then here you can see the cables for the sky train as well as the rocket boosters as it was about to land on Mars. So then what we're doing is we're testing different re-entry methods for landing our rover. And so we were testing parachute, we were using a parachute, and then we're going to try propellers, which haven't been used before, as well as rocket boosters.
Okay, now for the physics behind the project. Our project deals with two types of forces, acceleration forces and deceleration forces. And as you can see, for the acceleration forces, we have gravity. In the deceleration forces, we have air resistance, a parachute, propellers, and rocket boosters. And gravity is the force pulling down on the object as it is falling, and the acceleration of gravity on Earth is 9.8 meters per second squared. And as you can see right here in this picture, the increments between each one of these objects gets larger and larger, and that is a result of the acceleration of gravity, and the increments of this is 1 second. And the next force is air resistance, and air resistance is the force pushing upward against gravity. And if air resistance equals gravity, then we will get the net force of 0. The net force of 0 means that we reach terminal velocity, and terminal velocity is that we're neither accelerating nor decelerating. We're traveling at a constant speed of falling. And the first deceleration factor that we added was a parachute. And a parachute helps with slowing it down using air resistance with a wider surface area and a dome-shaped thing for the parachute. And this captures more air as it is falling, and we are using the parachute also to orient our object. And the second deceleration factor that we added were propellers, and we were using dual-bladed blades for the propellers. And if our object were to fall fast enough, the propellers themselves would spin just by themselves, but we did not have a good enough height for that, so we needed motors and engines to go with these propellers to help increase the speed. And the last deceleration factor that we added is rocket boosters. And these rocket boosters, their peak is 12 newtons, which is the energy that they're giving out, and then this energy decreases to about 5 newtons, and this goes on for about 0.5 seconds, so all of the energy is depleted out of the rocket. And this happens over a very short amount of time, and these are solid-state rockets, which means that once they are ignited, they cannot be shut off. And we would have a greater chance with liquid fuel rockets, because if we needed to shut them off, we could just cut the fuel to the rocket. And the way that these are lit is a wire is connected to an energy source, a battery, and the wire heats up. And on the end of the wire there is a substance, which is, I believe, mostly gunpowder, and this substance igniting the rocket.
And then the reason we chose the B60 engine is because, as you can see from the force, how it goes up and then it remains steady. This part right here is why we chose the B60 engine, because we thought that it was better. Like, a lot of them just peaked and then just went straight down, and we needed that leveling force and like the increased amount of time to help that out.
We had a graph on here that showed it had a slope like this, and it would level out down here, and that's essentially reaching terminal velocity. And the graph showed the velocity, the velocity right here on the y-axis and the time on the x-axis, and we predicted that the fall from the building would stop at about 1.1 seconds, which is about where it would level out on our graph. So we might have reached terminal velocity with our object, just with the rover and the object itself, nothing else added to it. And the design, we were originally going to go with this, but then we switched to smaller blades because I'm not actually sure why we switched to smaller blades. I think just because it would have too much propulsion and thrust. And because we switched blades, we had to switch the motors. And this platform right here is where our object would actually fit, the rover, and then the rockets were attached right here. And we would have this right here, so the kickback that the thrust comes out right here, so the parachute in the actual model rockets that we launch can come out are blocked off, so we don't have that, so it doesn't disrupt.
Okay, so with our launch, we didn't receive our motors in time, so we were unable to launch it. And also we relied on some people to get some stuff done, and they were unable to achieve that in time to let us launch our rover off the roof. So, but from the mini tests we did and our calculations, we believe that the parachute would have worked as planned, and it would have done its job, which is not only to decelerate it, but also orient it so that if there was a problem with the rocket boosters and one of them went off a little too early, it would prevent it from running into the building. And so we believe that it would have done its job well, and then also we were trying to be cost effective, and we did a good job of doing that. We did not spend as much as we had thought we were going to, because that's made out of aluminum, so that was also less expensive as well.
And the reason that we shaped it like this is because all the weight is down here, which gives it a good center of gravity. So when the parachute is deployed, it doesn't move back and forth, and it's easier to hold like this than like that.
Alright, and so then what we would modify is the propellers. Although we thought they'd be a good method on Earth, they might work, but the problem is on Mars, the air is way thinner and less dense. So the rotations of the propellers wouldn't do as much to decelerate it, and so we believe that that method, although it was unique, was not a good decision. That would not have worked very well. And then the liquid fuel rockets would have been easier to use than the solid rockets that we use from Estes, because once you light those, you don't have control over them, versus like liquid fuel rockets, you can add fuel or take it away, and you can do what you want with those. Also, like time, we ran out of time, which isn't uncommon. Sometimes NASA has issues with time and stuff. So, but next time you would know for the future that we need more time than you would predict, so you have to get going a little faster. So we'd like to thank FSI. We're so glad to be here and glad that we have this opportunity to explore this type of engineering, aerospace engineering, and construction of a way to land a rover. And I would like to thank Excel Energy for founding my research and allowing me to create such a cool project that's over there. And Chesapeake Energy Foundation for supporting my stay at Belford Hall and here at UNC and giving me such a great opportunity.
And I would like to thank the Kinder Morgan Foundation for funding my research here at FSI. And I would like to thank my family for paying for me to be here so I can do the research that I am doing.
And then we really need to thank Maurice Woods. He helped us so much with the CAD software. We designed the frame on the software that took like 4 research days, and it was very frustrating for Maurice, but we're very grateful for him for helping us create that and going through so much stress and just helping mentor this project.
And we had Dr. Seaman on here, but
yeah, Dr. Seaman helped us with the math modeling of it, as well as, like, if you just had any questions, we could go to Seaman, because he's really relaxed on that. Any questions?
Nick.
I'm still intrigued by the concept of the inner Martian atmosphere and the fact that Martians have to did you guys do the models too, kind of larger propellers or higher power motors? Good work in the atmosphere. And how much more is the Martian atmosphere than in the Earth atmosphere?
We do not know that. All right, the question was, I forgot.
The question was like the difference between the air densities and like the thickness of Mars. So would there be propellers and motors that would be able to work?
Yeah.
Well,
is that the engineering challenge?
I mean, I think it is possible if you had a lot of time. I think it just depends on how long the blade is as well, because like even if you bring a longer blade in, that might help as opposed to like a smaller blade, because we did switch our design from a larger blade to a smaller blade before we thought about that a wider blade would rotate in a bigger circle, so it would displace more air, which would in turn slow it down. So yeah, I think that's something that could possibly be overcome.
But with that, we would have to include bigger motors and bigger engines to propel the propellers. Shift.
What are the purpose of those four crosses with circle in the center? Is that something that your first time you didn't have those? But when
That is.
She was wondering what the purpose of the four beams and then the circle in the center is, and you can kind of see that on here.
I believe the main purpose of this was so that we can keep the object, the rover that we were going to use, intact or keep it there, hold it stable.
And it's also like that way we can set the when you set the parachute there, you can set it like above it so that it doesn't, when it flies up, it doesn't fly too fast and then tilt it too much and then it could run.
How much more effective is it to like have all these motors and rockets and things onto your rover? I'm just like wondering, like, is even though like you have like better, more accurate placement, even like malfunctions of like motors and stuff, and the weight of them going off Earth, like, does that make up for like the accuracy that you would lose with airbags?
So you're wondering if, so your question kind of is, do you think that airbags or like this new technology and like propellers and stuff like this, is it worth it to program it instead of doing something like airbags if you know it works? Yeah, it's definitely a lot more difficult, especially like electrical and mechanical creating it, but I think it is because, especially for NASA, if they were to actually use a design like this, it could tell you, it can land exactly where you want it to go, and then as opposed to when you guys saw it bouncing around up on the screen, that's not very predictable, and although it does work relatively well, it just depends also on cost, too. You have to think about cost, and I don't know if it would be more cost effective or not just to do the airbags versus the new technology ideas we have. I don't know about the cost on it.
Mm-hmm.